Okay. Yep. I'll wait for that. Hello and welcome to the Monday seminar. I am Chris Marone and I'm super happy to see you today. This talk is going to be given by Audrey. Bonnelye. You can see some details of that. The formal announcement is always, I don't know, done for me by email. And we are very lucky that this has been a seminar series that's been going on for quite a while now. So there's a core group of people who know that our normal status is, our normal mode of operation is to mute ourselves at this point. But also to feel encouraged to just unmute and ask points of clarification along the way. And then at the end, we'll have a dedicated period for more detailed questions and answers and discussion. So yeah, without anything further, I would like to thank Audrey for being here and putting together a talk for us and giving it to us by Zoom, which is not the favorite way for anyone to do this, but it does allow us to get together. So thank you very much, Audrey, and I'll turn things over to you.
Thank you very, very much, Chris, for this invitation. And I'm extremely happy to present you some piece of work that I've been doing for the past 2 years now, since I moved in Nancy. And so I'm going to talk today about scales in rock mechanics and different experimental approaches that it's possible to develop to have a better insight on all of the topics that are for interest of people doing rock mechanics in general. So maybe first a little bit of introduction on why it is so important to discuss about scale in rock mechanics. So I think that rock mechanics is one of the only disciplines in mechanics that requires such a broad range of scales. On my screen, I hope that people can see my mouse on the screen. So we know that rocks are very complex due to their nature. Because they are made of an assemblage of different minerals. And so it's important to understand the link between the microstructure if we want to understand things at a bigger scale. Those bigger scale can be the scale of the underground, of the underground tunnels, for instance, or even of the fault. And I think that it's one of the unique disciplines in which we have to go over more than 10 orders of spatial scale, from the micrometer scale up to, let's say, okay, maybe I'm exaggerating a little bit, but let's say the 1,000 of kilometers. And I'm solely mentioning the spatial scale and not even touching the topic of the time scales. So we have to understand those complex material with various compositions and structure that can give some specific properties to the material. And I think of anisotropy, for instance. And also we need to do experiments because those conditions, underground conditions, are very hard to reach and nobody can go there directly and see what's going on. And we know that we have to go over a very wide range of pressure and temperature conditions. I'm definitely not the first one trying to tackle those topics, and especially the topic of doing some experiments. This is a paper of Griggs that was published in 1940, and he was describing at the moment the relevance of doing experiments in order to understand what's going on in terms of deformation inside of the Earth, and he was emphasizing some of the parameters that are relevant if you want to understand what's going on below our feet. And just to mention those ones, so he's talking about confining pressure, so the depths at which we are looking at the phenomenon, temperature, time dependence, and also chemistry and potentially the shear stress. So over the past year, I've been developing and I had the chance to collaborate with many different people. And I've been touching many different apparatuses and trying to develop an approach over part of the scale that I've been describing so far. So from the micromechanical approach, then there is what I will call later on the classic mechanics. So with triaxial cell, I will introduce today giant experiments with our new apparatus. And there are also the in situ scale that is extremely relevant and that can be included in the set of different kinds of experiments that we can perform. So today I'm going to focus on the micromechanical testing. And I hope that it will convince you that it's important to look at the microstructure and at the micro deformations. And I will try to link it together with what I call giant experiments. And I will give you an introduction of the different things that can be done with our new apparatus. So let's go back to the basics of what we do when we do some mechanical experiments in the lab. And the work I'm going to present here is the work of Mathieu Lucéran, and you can see his picture on the top corner of the slide. Mathieu is based in École Polytechnique in France, and I'm one of his supervisors. So what do we do when we deform a rock? Basically, we take a sample that can be of any size, but mostly of centimeter size. And then we apply a deviatoric stress on our sample. And we usually measure the deformation. So you can see the evolution of deformation as a function of the applied stress on the sample. We measure actual deformation, usually radial deformation, by putting some strain gauges on our sample. And then we do deform it. And along the experiment, what we can also do is measure the evolution of p-wave velocities. The problem when we do such an experiment is that we are solely considering deformation as a punctual value because we are usually gluing some strain gauges on the sample. But what we know is that deformation is not a single value on a single point. And for this reason, over the past year, some people have been developing some techniques based on digital image correlation, which means that we are deforming some sample, and we're following the deformation with a camera, or in our case, with an SEM. And what we are trying to and sort of succeeding of doing to do with Mathieu is to combine the use of digital image correlation together with active acoustic acquisition in order to have a full view of the full field of deformation and try to combine it with something that we know that happens and something that we're used to measure when we're doing rock mechanics, and also to be able to compare it with what people are trying to look at on the field. So the idea of all of that is to have a better insight on how you can localize deformation, what are the different mechanisms, and can we somehow quantify it both with full field deformation and acoustic acquisition. So what we do measure, so first we are loading a sample. So this is a machine, but I will show more slides and more description of the loading apparatus. So we are uniaxially loading some sample, and we are doing that directly inside of an SEM, which is an environmental SEM. And we are measuring the force, the displacement, and the full displacement field thanks to digital image correlation. We're controlling the temperature and the hygrometry inside of the SEM. And in the meantime, we are measuring the evolution of p-wave velocity, both axially and laterally, with respect to our sample. So here is how things are looking like. So we have a tiny little sample of parallelepipedic shape, of 8 by 8 by 16 millimeters, and we are ion beam polishing the surface. We're using an ion beam polishing device because the sample that we are using are clay, and so we need a very fine polishing if we want to be able to see the very fine microstructure of our sample. So you can see both a scheme and a picture of the assembly. So we are measuring the P wave velocity all along the experiment, both then actually and radially to our sample. And then we are, so then what we do with all of that is that we are putting everything in ESEM, and we're loading step by step our sample, and we are making some pause during the loading in order to be able to take some images directly with the ESEM. You can see the relaxation between each step, which is very important because we're taking high resolution images. And so we need the sample to be extremely stable to be sure that we are not, that we don't have any noise problem in the picture that we're taking. So in that case, we are loading a sample with a bedding orientation. So the bedding orientation is perpendicular to the loading direction. So those experiments are extremely time consuming, meaning because, like, first of all, because of the time that is required to take the picture, and also the time that is required to reach the appropriate conditions in terms of temperature. So we have the good hygrometry inside of the chamber of the SEM. So he's been loading his sample, and you can see the stress strain curve on the right that is corrected from the deformation of the vessel. And so all of the S1 to S8 steps are the steps and the image step that he did. When you do that, you can have a wonderful picture. So on the left side of the screen, you can see that I hope that you can see moving. You can see the difference between the image 1 and the image 8 that he took. And you can see that, so first of all, it's a clay-rich sample. So you have in dark all of the clay particles, and in light, all of the more solid particles that can be quartz or calcite, and a little bit of pyrite as well. What you can see is that you can observe different types of mechanisms. So closing of some fractures, some shearing as well, and also some opening. So which is what you can see on the left. Then once we have those images, we are doing the digital image correlation. It consists in making a sort of virtual grid on your screen, taking some correlation domains that are some squares of some pictures, and then you're trying to look in the deformed image to the position of the same square in the initial image. From that, you can calculate the displacement of that square, and this will give you the full displacement field, which is shown here, which is transformed first in equivalent deformation, and which is showed on the picture on the right, where you can see with the color map the equivalent deformation of the matrix in your sample. So
it's Chris. Just a quick question, if I may. Can you go back one more slide from here?
Yeah.
These steps, S1 through S8, those are time-dependent relaxations. How does that happen? So the stress goes up, and now it goes down with strain. Yeah. And those are
because we're stopping the machine, we're stopping everything, so that we know the stress state when we are doing each image.
I see. Yeah. So, but it's relaxing.
It's slowly relaxing. Just a pure relaxation.
Right, and the boundary condition is constant displacement of your load point or something.
Yeah, exactly. So it's not creep. It's so we stop the displacement, and which is why you can see the stress relax.
Yeah. Okay. Thank you. Yep.
So yeah, if there is more questions on the techniques, I mean, anyone can jump in and ask questions. So, well, I mean, doing those experiments is very nice, of course. Otherwise, we wouldn't be doing it. The only thing, and it's really cool because it gives you an insight of what are the mechanisms that are taking place and where they're taking place. The idea behind that was to try to understand where in the rock they would take place. So we decided to take different subsets in the image in order to see whether there could be some zones in which you could have some preferentiate localization of deformation. So we choose 3 different zones. So you can see them here. So there is P1, P2 up there, and P3 here. And so they were chosen with respect to the composition of the minerals that you could see in it. So some place where you have very tiny particles, and some place that are at the interface between some bigger particles and the clay matrix. And so from that, around those different contours, he has been calculating the total deformation as a function of the stress. So the vertical axis is here the stress, and in horizontal you can see the evolution of the deformation, knowing that it's classical mechanics convention. So no, it's a rock mechanics convention. So compaction is taken positive, and dilation is taken negative, as we usually do in rock mechanics. And so what we do see is that apparently it seems that the biggest deformation is localized at the interface between the soft matrix and the bigger particles. So during our experiments, as I mentioned to you earlier, we've also been measuring the evolution of P-wave velocity, which is used usually as a proxy to understand compaction and dilation. So usually compaction, I guess that everybody sees what it is. It means that we are compacting all of the pre-existing porosity that can be divided into like classical porosity and crack porosity. And usually dilation is associated with the generation of damage inside of the sample. So here in black, we can see that we have the evolution of temperature, which is correlated to the relative humidity, because we are inside of the SEM. We can see in green the evolution of the axial stress with the relaxation steps, and in blue and red the evolution of velocity. All of that is taken as a function of time, and we can see that we have an evolution of the variations of velocities together with the loading of our sample. It can seem a little bit weird, but we can discuss that later. So what we see is mostly a compaction, because we see an evolution of an increase of the P-wave velocities all along the loading of our sample. But we see that toward the end of the experiment, so close to failure, we have a different evolution of our P-wave velocities. So we have, during our steps, some decrease of the velocity linked to the damage, but we also observe some recovery that is linked actually to the relaxation steps. And actually, so we observed that previously while we were doing some step creeping experiments during the PhD of Geng in 2018. So this is a very, the behavior that we see is very similar to something that could be done under triaxial conditions and some evolutions that we have observed previously. Also, if we correct everything and represent now the velocities as a function of the strain, we see a classical behavior, meaning that we can observe the compaction, and at some point we start to observe the decrease when we leave the linearity of the stress strain curve. But actually, this allows us to compare what is happening inside of the P-wave velocities with what we've been observing in the different phases of the material. So we do observe the compaction. So we see that all of the stress strain curve that we've been presenting earlier are going toward compaction. And so we see that all of our P-wave velocities are actually increasing. But then when we enter in the phase 2 of the deformation, so when we start initiating the damage, so which is an equivalent to the C star value, we start to see a different evolution of the P wave up to the moment when we decrease, which is reached prior to failure. So far there is nothing brand new, in the sense that what we are showing is like we're putting together some pictures that are showing the full field together with the evolution of P-wave, but we're not very far away from trying to have a quantitative approach that will link the variation of P-wave with a quantitative way to discriminate all of the different mechanisms of deformation that are taking place. So we hope to be able to link a percentage of increase in P-wave velocity with a percentage of compaction, and most of all, a percentage of damage that is generated, in order to be able to understand when we will reach the critical point where the rupture, where the deformation is going to properly localize and be ready to make the sample fail at the macro scale. So this part was to show what is happening at the micro scale, because I think it's not a very common way of looking at things, and I hope to show you that we can link, and in the future we will be able at some point to link what is happening at the micro scale with what is happening at a way. Let me introduce you our new machine. The name of the machine is Dimitri, and the acronym is actually very French, which means device for triaxial analogic modelization. So since 2 years now, I moved in a department of geosciences and civil engineering, and my colleagues who are more coming from the civil engineering community have been developing that device. So I'm teaching at the School of Mine, and the machine was initially created to make some physical models of underground mines. So you can see on the picture, the big yellow thingy is the crane that we need to use to carry all of the pieces of the machine. And on the top of that thing, you can see the whole machine, where you have 3 different sides that are moving in order to generate a true triaxial stress state. So I'm going to describe it in more details a bit later. So experimental, there are many different ways to discuss, to do some experiments. And so, well, to simplify things, let's say that there are 2 different ways. One can be the physical modeling, and it's something that is broadly used in civil engineering. The goal of physical modeling is to make some tiny little models that are not that tiny, but in which you truly mimic the reality, which means that you need to scale all of the parameters, and so you need to use analog materials in order to do your experiments. So, for instance, on that slide, you have a tunnel that was made with some bricks in order to see the collapse that can take place depending on the orientation of the joints of the structure. So you can see that depending on those joints, you will have a different type of collapsing inside of your physical models. So as I mentioned, this requires a lot of efforts in scaling of the parameters, and I will discuss that later. But this allows a direct comparison between the model that you've been generating and the reality. Then there is, I didn't know how to call those ones, but there is the classical mechanical experiment. I call them classical because that's what I was doing during my PhD. So I'm very much used to it. And in those experiments, the goal is more to take a tiny little sample and put that sample into the pressure and temperature condition that you can actually find in the crust. The philosophy behind that is to reproduce in situ conditions and to identify some physical processes that are responsible for deformation and rupture. And so in my presentation, I'm going to try to present you 2 examples of experiments that we've been performing in Dimitri that are trying to follow those 2 different philosophies. So this is another picture of our machine. So that machine, I told you that it was a true triax because in our case, we can apply a sigma 1 different from sigma 2 and different from sigma 3, sorry. So here you have one of the moving sides. At the back, you have the second moving side. And on the right of the picture, you have the top side that we need to put on the top of the vessel to apply the last component of the stress. As I mentioned earlier, this machine was designed to look at the mechanical behavior of underground structures. So we also have an excavation, 2 excavations windows that are on the fixed sides of our vessel. So basically, the machine was designed to put something on a stress and then drill inside of that block. So the size of the block is 1.5 by 1.5 by 1 meter. And we can discuss of the possibility of the machine. So here you can see a scheme of the block that we can put inside of the vessel. Here are the windows that are made for excavation. So we can put blocks that are up to, as I mentioned earlier, 1.5 by 1.5 by 1 meter. We can reach a maximum displacement on each side of 10 centimeters and a maximum stress on the entire surface, on each entire surface of 1.5 MPa. We can control the machine by force or displacement rate control. Each side is equipped with 4 cable displacement sensors. And we have different acquisition systems so far. So one that is made to control everything, like the force and the displacement, and also some new sensors, but I will discuss that later, with a low frequency of acquisition of 1 Hertz. And also we have some high frequency acquisition systems that are allowing us to measure stress with strain gauges and temperature with thermocouple with a frequency, with an acquisition frequency of 6 kilohertz. I mentioned to you earlier that the machine was designed to look at the mechanical behavior of underground structure. So there is a whole excavation tool that was developed, and that machine allows us to excavate. So during, like while we're under stress, and to excavate some tunnels with a squared shape. So this is why it has a specific, you have the main tool here and you have some small tools on the side. So it's digging at the beginning something that is very circular, as usual when we dig. And on the side, we have some wheels to correct the square shape, to be as close as possible from the shape of tunnels that are usually excavated, sorry. So because the machine is big, it can't apply a very high stresses. So at some point, there has been some discussions of what kind of material can be put inside of the vessel. And this is the work of my colleagues. They've been working for more than 5 years now on what kind of material they should put inside. And I will first show you a video to show you the printing process of 3D printed sand, and then I will show you the possibilities that it's giving. So, up. So 3D printing technology is very useful because then you can impose the geometry that you like to your sample. And in that case, it's a 3D printed sand that is put, that is done. So we put some layers of sand, and we put some layers of glue in order to link the whole process. So this process was initially made for the industry, for the metallurgy industry, in order to be able to make giant shapes for the metallurgic industry. This specific process is giving many, has many, oops, sorry. It's really nice because you can generate the shape that you like, but we are reaching the limit of the technology in the sense that we want to have some material with very low mechanical properties, and so we are putting the lower value, the lower limit amount of glue inside of our samples, so they are extremely weak. Okay. So let's go to the to see how the material looks like. So I didn't put a full description of the mechanical behavior of that material, but I invite you to see the first tests that were done by Jaber et collaborateurs on some more classic 3D printing technique with some plastic 3D printing. And you can also see the PhD of Emilio Abillad, where he's been solely working on developing and understanding the mechanical behavior of that 3D printed sand. The advantage of that technique is that then you can print something with very complex shape. Here you see one discontinuity. So it's the model of the discontinuity. You can impose some kind of roughness on your surface. And here you have some rock bridges in order to make the sample hold as one block. And here you can see some tests that he's been doing, so those were uniaxial tests, and one of the problems of that material is that it has an orthotropic symmetry, which makes it very tricky, let's say, to understand. But one of the biggest advantages is that it really behaves like a sandstone, but with very, very low properties. So it's a very appropriate material if we want to study underground excavation, for instance. And then what we can do is to print some discontinuities, so different set of discontinuities with various orientation, and reproduce the experiment as many times as we want, if we do have the money, because it's quite expensive. So the idea was to 3D print, and so what we've done actually is to 3D print the first blocks. So we've been 3D printing 3 different blocks from T1 to T3, one with no discontinuity, one with just one discontinuity, and one crazy one that more looks like a puzzle than anything else. And because the sample is quite big, so it's a cube of roughly 50 centimeters by 50 by 50. And the idea is, okay, so we want to drill inside of that sample, but first it's too small to get inside of it's too small to reach the borders of our machine. So we've been putting some dense polystyrene around it to decrease the volume of our the volume of the machine. And we've been trying to work on how to insert some sensors, because when you have a big machine and just sensors outside, you don't really know what's happening inside, and what we are interested in is what's going on inside. So we've been inserting some sensors, some force sensors inside of the material in order to see whether they can measure something. And actually they do measure something. So all of those curves are showing the evolution as a function of the applied force of the measurement inside of the sensors. And we see that when we load it hydrostatically, our sensors are responding. We are not fully sure yet of what we do measure, because it's a very complex, there is a very complex interplay between our samples, who are very soft, the sensor, and how to insert the sensor directly inside of the material. But we see that we have an evolution, and actually when we start drilling in the machine, in the sample, so here you have an evolution of the excavation length. Here it's the evolution of the measurement of the approach stress measurement inside of the second slice. And we see that when we approach the excavation tool, when we start digging, we see an evolution of the stress, and actually the stress is increasing, which is what we're expecting, because you have the stress that is going outside of the excavation zone. We can also do some post-mortem observation. So from the intact slice toward the one that looked like a puzzle from the previous slides. And we see, for instance, that as long as so here is how the excavation looks like. So you can see that it's actually truly a squared tunnel that we're drilling with the rounded shape at the very end of the block. And we see that in the case of our experiment, we just see some blocks that are falling after the unloading of the whole experiment. And I can make some partial conclusions for the moment. I think that we can see that 3D printing techniques are very promising to study the mechanical behavior of complex rock masses. The thing is that we can now print as many discontinuities in the blocks as we wish, and we can reproduce our experiments. We need to have a better control on material properties. So this technology is quite new, and we need to have a better control on it. And we need to do more work regarding the instrumentation, like how to measure force or stress and how to measure the deformation. And so we need to do some more work on how to integrate directly some sensors inside of the material. And we can discuss that a bit later. I think that it gives us many perspectives. The second application, I think that many people attending the seminar are very familiar with all of that. And so it's not, I mean, it's far from being new because it's a paper from Bonnelye and Brace. Many people have been working on how to characterize the evolution of friction along a discontinuity, and that are making some analogs to earthquake cycles. And so they've been doing it for the first time in triaxial experiments, where they put a discontinuity inside of a sample, and then they're loading it and checking at the influence of all of the possible parameters that you can ever imagine. So stress state, temperature, material, etc., and etc., etc. So some people, and among those people, of course, Chris, have been developing some shearing apparatus in order to investigate more easily those parameters, more easily in the sense that they have a better control. So you have the double shear experiment that is presented here, and people have been doing, again, many experiments toward that direction. Many people have been starting then to have a look at what happens if you put bigger blocks, because one of the limitations of those of the experiment that were done is actually the size of the sample. And so there are some phenomena that you can only see on a bigger sample. So here's an example of some work that is done in Japan to look at the sliding surface. And in earth science, I said earlier that analog modeling is more something that's done in civil engineering, but there are also some attempts of doing some analog modeling. And I'm putting that example to make an analog version of a subduction zone. with specific material. So usually analog experiments are done in sandboxes, but in that case, it's a foam experiment that was done in order to reproduce the complexity that you can find in subduction zones. Our idea is to try to do something a bit similar in our machine, and we've done some very preliminary tests with the students, and I'm using all of the students here to help me to carry those blocks that are very heavy. So we decided to do those experiments on polystyrene. On high density polystyrene, so the density is of 50 kilograms per cubic meter. It's the highest density polystyrene that I could find on the market and on those very large blocks. So this time we're almost entirely filling the machine. We made a discontinuity in our material, and we placed some strain gauges along the interface in order to see whether we could measure something. And we've been doing some experiments by controlling the horizontal displacement. So from one side, just to make one part of the polystyrene go up the other, and to have a look at the friction on that interface. So why polystyrene? Well, first of all, because it's cheap. I wouldn't say really cheap, but it's one cheap way to do it. Also because of the weight, because those blocks are huge, and despite the fact that we have a crane to carry everything, in our case the blocks are too big, so it's not that easy to use the crane to put everything inside of the vessel. So it means that we can carry it by hand to put it in the vessel. And then there are the real reasons. So first, polystyrene is a porous material, which means that we can observe some compaction prior to the sliding on the surface. Then it can generate acoustic emissions. So I'm not going to show you some results from the acoustic emissions that we tried to measure. Because it's still some work that some parameters need to be adjusted. And also, last but not the least, because it's polystyrene, it has very low elastic moduli, which means that all of the physical processes that are taking place during the sliding of the sample are going. Everything is slowed down due to the fact that we're talking about very low elastic properties. And now, just briefly, I will show you some sort of preliminary results. So it's just the raw data set that we have because everything was performed very recently. So on the bottom part, everything is as a function of time. On the bottom part, we can see that that we are measuring that we are controlling the displacement of our sample at the rate of 1 millimeter per minute. And so we can see that we can, move the whole side, and that it's moving roughly the same way on the whole side, and that everything is homogeneous, and that we can apply a constant load on the side that we're pushing. And we can see that we can measure something on our strain gauges. So some of the things are looking very weird so far. So we need some further work to interpret it. But if we zoom in a little bit, so on the same experiments, and again, the different colors are the different strain gauges. So from the bottom one to the top one, and we can see that it seems that we can observe some sliding of some parts of our experiments. In our case, we are simply having one block going on the top of the other one. And the only thing that is applying vertical stress is just the weight of our sample, which means that it seems that everything is generating at a specific part of our block. And we hope that we're going to be able to track different types of signals from one strain gauge to the other. And actually, we see that from from that strain gauge to that strain gauge, we could potentially track potentially the evolution of the sliding. And we see that if we try to go faster, so 10 millimeter per minute, so 10 times faster, we observe a very different behavior. And actually, we could even hear it, and we could hear some noise when we were moving much faster. And so this is leading me to my partial conclusions. So I think that polystyrene can be an analog material, and I'm very happy of that because it means that we can use that to calibrate our machine and to test many parameters. The device is actually suitable for this purpose, and it's good because it was not designed for that. And it means that we can go for more complex geometries and than what was done in the past, and look at the influence of stress heterogeneity, for instance, or various stress orientations, because we are under true triaxial conditions. And so more work needs to be done regarding instrumentation. I mean, it's the same conclusion as previously. Now we need to focus on how to measure force or stress close to interest zones, and how to measure properly deformation on the whole surface and not just on the side. And for my very preliminary, more general conclusions, I mean, they're roughly the same. I think that what is interesting is more the perspective that it gives. First, it will give us very interesting perspectives toward experiments and how to integrate sensors to be able to be as close as deformation, for instance. But given the size of the machine, we can truly compare with what can be going on in situ. And I'm thinking of comparing things directly with seismology, with broader range of frequency of sensors or fiber optic measurements that could be directly compared and inserted inside of the materials that we're using. And also, we can use the machine in different setup and conditions. So what is very nice is that we can go toward 3D stress states, but also given the setup, we can also have a small step back and compare what we do with what other people do. So I've been mentioning the giant machine that is developed, the giant machines, sorry, that are developed in Japan, or what is done by some group like the one of McCleskey, for instance, in the US, because they're using also some 2D stresses states and see if we can have comparable observations and then insert them in the 3D stress states. And I hope that we can go toward upscaling, but also downscaling to link with what I've shown during the first part of my talk. I hope that we can also use some image correlation techniques in order to also have an understanding of what's going on at the small scale and how it's evolving and the evolution toward the large scale. And so with that, I will thank everyone for their attention, and I will mostly thank all of my colleagues. So Olivier, Marianne, Emilio, Delphine, and also all of the students for their help and for all the discussions. And I'm ready to take questions.
Mm-hmm. Wonderful. Thank you very much, Audrey. I will invite people to unmute and turn their camera on if you'd like, whatever you would like, and join me in thanking Audrey for really interesting talk, very nicely put together. Yeah. And while she is catching her breath, I recommend to you to use this feature at the bottom of your screen. You can raise your hand. That helps to put us in some order. But please join in the discussion. While you are thinking about it, I have several questions, and the one that falls toward the end of the talk is on slide 22. Audrey, you showed us, I was confused because I expected to see a circular hole. You're drilling into this, but it produces a square opening? Yeah.
Yeah, well, that was a will of my colleagues to have something able to make square holes. So if we go back to the picture of the tool, so it's